Hello. Good morning. We're going to look at this lectures on scaling laws. So this document discusses the concept of scaling laws, which are essential for understanding and designing systems at very small scales, such as microsystems. So what happens when something is scaled up or scaled down, scaled to a very large level or scaled down to a very small level? That's what scaling law is all about. So scaling laws describe how physical phenomena change with size. They're crucial for designing microsystems where normal engineering intuition may fail. So historical context. Galileo Galilei's early work on scaling laws, including his famous lecture on Dante's model of hell, is highlighted. So this is a very interesting paper. His observations on the strength of structures and the scaling of biological forms laid the foundation for modern scaling laws. So here are the key concepts, as you can see: geometric scaling, perimeter, area, volume. This scales as L, L square, and L cube respectively, where L is the length scale. Surface area to volume ratio, so scales as L inverse, because surface area we know L square and volume L cube, divided gives us L inverse. This has significant implication for phenomena like heat, dissipation, structural strength. Then we have mechanical scaling, cantilever beam. The stiffness of a cantilever beam scales linearly with size, but smaller beams behave stiffer under their own weight. So when the beam becomes very small, then its behavior changes. Then we have columns and buckling. So the mode of failure can shift from compressive failure to buckling as the size changes. So this demonstrates allometric scaling. Then we have micromechanisms, localized compliance. So this is to simulate joints in micromechanisms with different scaling behavior depending on the configuration. Then we have dynamical scaling, displacement, velocity, acceleration. This scales as L tau inverse and L tau square inverse. Natural frequency increases with miniaturization, allowing microsystems to operate at very high frequencies. We have in fluid mechanics, Reynolds numbers, scales as L square, affecting fluid flow characteristics in microchannels. Then we have surface and tension, predominant at microscales, including phenomena like capillary action. Then we have electrical parameters,